Hi everyone. So we're going to talk about probability a little bit. And this is a really interesting subject. It's something that's very applicable. Just think about the word probability or probably or chance. It's something that you think about just about every day. I mean, this could be something like, oh, it's probably going to rain today. Now that's a little bit informal. Now what you can mean maybe more specifically is there's an 80% chance of rain today. So we have this kind of intuitive sense of what probability is, and we use this intuitive sense just in our language, in our decision-making process. So that's why probability is so important, is because most of our decisions are based on maybe not a very rigorous mathematical probabilistic analysis, but at least some sense of, okay, this is likely, this is not likely when we decide whether we're going to do whatever it is we're going to do. So of course we're going to take the mathematically rigorous perspective and look at probability in some very simple examples or experiments. But the cool thing is by studying probability, even in simple examples, it will help improve your decision-making process. So it's a very cool subject to think about, and let's jump right in. All right, so here are some of the key words when you begin to talk about probability from a very rigorous mathematical perspective. Not just, oh, it's probably going to rain, but actually going into where do we get these numbers like 40%, 35%, etc. So probability always begins with an experiment. And I think the best way to kind of define these words is to just give you a concrete example of each one, and then we'll do several of these, and I think that the kind of big picture will come into place. So we want to start with an experiment. And so for our experiment, I'm going to think of the simplest thing I can give you, which is flipping a coin one time. So that'll be our experiment to kind of illustrate the definition of these other aspects of probability. Okay, so other examples of experiments, rolling a dice, maybe even just walking out the door could be an experiment. And so what makes an experiment from a probability perspective is that there are outcomes. Okay, so I do something, I flip a coin. What are my outcomes? Well, my outcomes are heads or tails. So my outcomes are just what can happen after I perform my experiment. And we're going to make an assumption, and this is maybe just kind of a technical point that you can gloss over for now, but it is really important. We're going to assume in the experiments that we cover that all outcomes are equally likely. So we'll put a little star here, that we will assume all outcomes are equally likely. So what do I mean in the context of our experiment of flipping a coin? I mean that there really is a 50% chance that I'm going to flip a heads and a 50% chance I'm going to flip a tails. It's not an unfair coin. Some coins might be kind of weighted not uniformly so that it's more likely to flip heads versus tails. But we're not going to assume that. We're going to assume that all outcomes are equally likely. And most of the time, this is a fair assumption to make. So the next concept we need to think about is a sample space. And what is a sample space? Well, a sample space is just the collection of all outcomes in our experiment. So for flipping a coin, our sample space will just be heads, which I'll just write for H, and then T which I'll write for tails. And a lot of times the sample space, you just want to draw a picture of the sample space and just sort of, you can use notation or whatever you want to represent all the different aspects of the sample space, but you should just understand that when I refer to this H in the sample space, that stands for the outcome of heads, and then T will stand for the outcome of tails. In more complicated experiments, there's going to be a lot more outcomes in our sample space, but the sample space is just the collection of all possible outcomes, so it needs to be exhaustive. Okay, and so what is an event? Well, an event is a collection of outcomes from the sample space. So and now you can, of course, have more than one event. So, for example, I could just take just heads. Right? That's an event. So you think about, I have my outcomes and my sample space, heads or tails. An event is actually just one or more of those outcomes. So in this case, I'm just picking the one outcome, which is heads. That's my event. So you can think about this maybe a little bit more informally. I'm flipping a coin. I know that my outcomes are heads or tails. The sample space is just the collection of all those outcomes. And then I'm interested in an event. The event I'm picking is flipping a head. Okay, so I have a coin with me. So if I flip it and look at it, I flip a heads. I can flip it again, and I flip a tails. Okay, so I'm going to perform my experiment, and then I'm either going to get a heads or a tails, and then the event I'm interested in is flipping a head. So probability comes in and describes the chance or likelihood, typically as a percent, of a particular event occurring when I perform the experiment. So the probability of an event in the notation is typically the letter P, and then in parentheses we'll put the event. So I'm going to put probability of H, and now here again this is kind of shorthand, but I'm just saying the probability of flipping heads is going to be a fraction or a ratio. It's going to be the ratio of favorable outcomes to total outcomes. And now, of course, this is favorable outcomes in the sample space and total outcomes in the sample space. So if I just look at my sample space that consists of the two outcomes, heads or tails, there are a total of 2 outcomes. So when I'm thinking about the probability of an event, I always want to put the total number of outcomes in the denominator. And then for the particular event, in this case flipping a heads, I just want to count the number of outcomes in the sample space that are favorable to flipping a head. Now, this is a very simple example. Of course, there's only one outcome that's favorable to flipping a head, and that's flipping a head. So I'm going to put a 1 because there's one favorable outcome. So as we see, the probability of flipping a head is 1 out of 2, or 1/2, and a lot of times we just want to put this as a percentage, 50%. But of course 1/2 and 50% are the same thing, but I think in our day-to-day life we deal a lot with percentages when it comes to probability. Okay, so that's kind of the big picture. You have an experiment, you have outcomes, you have the sample space, collection of outcomes, and then I'm interested in a particular event, which is a collection of the outcomes from the sample space. The probability is just the favorable outcomes divided by the total outcomes. So maybe this is still a little fuzzy, but let's do another example, and hopefully this becomes a little bit more clear. Okay, so I'm going to set this up kind of in this way. So we're going to talk about what experiment we're going to be looking at. We're going to draw the sample space, which is going to contain all of the possible outcomes. And then we'll look at various events, and then we'll compute their probabilities by just looking at the sample space. So the next experiment I want to look at is rolling just one, so a 6-sided dice. And we're going to be dealing with dice in a few examples, so I guess I'll just say, well, I guess I should actually use the correct word before I talk about it. Rolling a 6-sided die. Okay, so the word dice is the plural of the word die. Okay, so if you have one die, that's just one die, singular. If you have two dice, that's dice, D-I-C-E, plural. Okay, so that's just a common mistake. You know, people say, oh, that's a dice, but actually dice is the plural of the singular die. Okay, doesn't matter. Rolling a 6-sided die. Hopefully you know what I'm talking about. I actually have a bunch of these. I was planning on having y'all roll a bunch of them in class, but I guess I'll just have to do it for you. Okay, so remember that our assumption is that each outcome is going to be equally likely. So somehow these die need to be uniform, right? They're cubes, so each side is the same side. The mass is uniformly distributed, blah, blah, blah. All you need to know is that each outcome is going to be equally likely. Okay, and what are the outcomes in our sample space? Well, the die is labeled 1, 2, 3, 4, 5, 6. So our sample space is just 1, 2, 3, 4, 5, 6. Here are all of our outcomes. So I can roll a die. I rolled it, it's a 2. That's one of our outcomes of our experiment in our sample space. And of course, 1, 2, 3, 4, 5, 6, that's all of our outcomes. So our sample space contains all of the possible outcomes. Here's another outcome. I rolled a 1. Here's another outcome. I rolled a 4. Okay, so what are the different events we can consider? Well, a simple one is, say, rolling a 3. Okay, so we'll put something like the probability of rolling a 3 over here. Well, I look at all 6 of my outcomes. How many of them are favorable to rolling a 3? Well, of course, there's only one, right? So the probability is 1 out of 6. Okay, this is very straightforward. You're probably thinking that I'm overcomplicating this, but again, the advantage of really thinking through these simple examples is that when we get to a more complicated example, it's going to be pretty straightforward to just find the probability by setting up the sample space. Okay, so I could replace 3 with any one of these numbers and the probability will be 1/6, but I could look at actually a more complicated event. So what if I said my event was rolling greater than, let's not put it that way, so rolling a number larger than, well, let's say 4. So now my event, okay, I'm going to roll the die, and the event is I want to roll a number larger than a 4. And just to specify, I'll say larger than means not including 4, so either a 5 or a 6. So now I look at my sample space, and I look at my outcomes, which ones are favorable to the event rolling a number larger than 4? Well, 5 and 6. So there are 2 outcomes that are favorable to rolling a number larger than 4 out of the total number of outcomes, which is 6. Okay, so the probability, this is a fraction, so we can simplify it, is 1/3. Okay, and I guess I told you that a lot of times we'll want to write these as percentages. So 1/6 is about 17%. It's a little bit less than 17%. 1/3 is a little bit more than 33%. But there we go. Now we have a percentage, and somehow we know how to interpret the percentage. What's the probability of rolling a 3? 17%. That's not very high, okay? 17% chance of rain. I may or may not bring my umbrella. I probably am not going to bring my umbrella. 33% chance of rain, rolling a number larger than 4. Well, that's a little bit more, right? So we kind of have this sense with percentages of how this works. So let me do one more that's a little bit crazy, but just to illustrate that these events can be really anything. So let's say the event is rolling a prime number. Okay, so we are going to, a little bit later, talk about prime numbers. But for now, I'll just remind you that a prime number is 2, 3, 5, 7, 11, 13, 17, 19, etc. Numbers that are only divisible by 1 and itself, not including 1. So how many outcomes are favorable to rolling a prime number? Well, 1 is not a prime, 2 is a prime, 3 is a prime, 4 is not a prime, 5 is prime, 6 is not a prime. So it seems like there are 3 outcomes that correspond to rolling a prime number out of the 6 total. So we get 1/2, and of course that's exactly 50%. Okay, so there's our experiment, rolling a 6-sided die. We have our sample space. We can list out some events and then compute the probability of those events. All right, so I'm going to try to take the training wheels off of probability. And rather than just every time thinking about experiment, sample space, outcomes, events, probability of events, all these vocab words that are important, I just want to look at a couple examples in the context of, here's a question. I want to know the probability of this. Tell me what it is. And then just sort of see how you navigate through writing out the sample space and looking at favorable outcomes versus just the total outcomes. So here's an example. If I roll 2 6-sided dice, okay, and here I'm using dice, which is the plural of die. Again, very common misconception. I think actually it's accepted to use dice either way, but I think the original intent is that die is singular, dice is plural. Okay, side note. So what is the probability of rolling at least 1 6? So this is a more complicated problem than the previous 2 examples. And now some of you may be able to say the answer. So maybe pause and just try to guess if you can. Okay, so I guess you'll see if you're right in a second. But I have 2 dice here, 6-sided. Fair dice, right? We're going to assume the outcomes are equally likely. If I roll them, I get a 1 and a 6. Okay, so this is an outcome of the experiment. I have a 1 and a 6. Maybe I'll record this down just so we have it. So I roll a 1 and a 6. This outcome is favorable to the event of rolling at least 1 6. Okay, now let me roll again. I rolled a 6 and a 4. that outcome is also favorable to rolling at least 1 6. All right, now here I roll a 3 and a 4. This is not favorable. So we have favorable, favorable, and then not favorable. Okay, so now you kind of see the idea of an event playing out in this example. So we have an outcome of rolling the die, we have an event that's rolling at least 1 6, and we can look at outcomes and say whether or not they're favorable or not. Okay. So how are we going to answer the question, what is the probability? Because we could keep rolling the dice and just get more outcomes, but that's not telling us the big picture of, okay, here are the total outcomes, here are the favorable outcomes. So let's actually draw the sample space, and I'm going to pull it up here, and you're going to see that from the sample space, it's not going to be too hard to read off what this probability is. Okay, so here's the sample space for the experiment of rolling 2 6-sided dice. And notice that I've listed the outcomes as pairs of numbers. So the first number will represent what the first die says, and the second number will represent what the second die says. And so now what I'm looking for, well, first of all, let's notice one thing, that how many total outcomes are there? And you can figure this out by just listing them out. We're going to talk a little bit more about counting later on, like how you count the total number of outcomes, but here it's not too hard to just list them out. I know that the first die can be a 1, and then the second die can be, well, whatever I want, 1, 2, 3, 4, 5, 6. The second die can be a 2, and then, the first die can be a 2 for this column, and then the second die can be whatever it wants, and then go on. So the first die can be 3, 4, 5, 6, and then for each one of those outcomes, the second die can be whatever it wants. So there are a total of 6 times 6, so 36 total outcomes. And that's important to know because that's going to be the denominator of our probability fraction. So now all we need to know is how many outcomes are favorable to rolling at least 1 6. Well, we can just look. So we see right here, that one's favorable because there's a 6. This one's favorable, 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 favorable. Notice that here, when rolling 2 6s, that is favorable, right? I could have said, what's the probability of rolling exactly 1 6? That would have been a different question. In that case, this would not have been favorable. But at least 1 6, if I roll 2 6s, that's fine, because that's at least 1. So how many total outcomes are favorable to rolling at least 1 6? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability of rolling at least 1 6, okay, so probability of event is 11 over 36. All right, so that's the probability, 11 over 36. And if you wanted to, I guess I'll do it for you, you can figure out what that is as a percentage. Let's see, calculator, 11 over 36. So that's 30.55555%. Let's just say it's approximately 31%. Okay, so just under a third of the time will I roll at least 1 6. Okay, so pretty cool. All right, so here's another example. Same experiment, so I'm rolling 2 6-sided dice. What's the probability of rolling a 10? Now, of course, what I mean by rolling a 10 is that I roll the dice, and the sum of the 2 dice is a 10. And you're not going to believe this, but I just rolled the dice and I got a 10, a 6, and a 4. So, I can roll the dice, and if I roll a 6 and a 4, well, I add them together, I get 10. That's a favorable outcome. Now, if I roll this again, I bet I'm not going to get a 10. Oh my gosh, I got a 10. I got a 6 and a 4 again. Okay, so that's unlikely. If I roll the dice again, okay, I rolled a 6 and a 3. So that's 6 plus 3. That's 9. That's not favorable. Okay, and I go through it again. Okay, 2 and 4. This is not favorable. Okay, so what is the probability of rolling a 10? Well, the easiest way to do this is to look at the sample space. So let's bring up the sample space. Okay, here it is. Here's the sample space. So now what I want to do, and I'm going to do something that's going to do a little bit more than just answer this question, is I'm going to sort of partition up the sample space by what the sum of the dice is. So if I look right here, kind of in this diagonal, the sum is going to be 2. Whereas if I look here, the sum will be 3. And then if I look here, the sum will be 4. And then if I look here, the sum will be 5. And then if I look here, sum is 6. And then along the main diagonal, it's getting a little bit messy. And the sum is 7. Maybe I should do this a little bit differently. Now, yeah, that was not exactly maybe the easiest way to do this. So let's look here, and then here, here. I mean, what I'm doing is I'm just partitioning up the sample space by what the sum of the dice is. So fill in here, kind of give it a checkerboard effect just so you can more clearly see these diagonals I'm talking about. So each one of these diagonals is going to have a fixed sum. So if I look here at this diagonal, the sum is 2. This diagonal, the sum is 3. This diagonal, the sum is 4. This diagonal, the sum is 5. This diagonal, the sum is 6. The main diagonal, the sum is 7. This diagonal, sum is 8. This diagonal, the sum is 9. This diagonal, the sum is 10. Then 11. And then 12. Okay, so there are all of our outcomes partitioned up by what the sum of the die is. So now it's really easy to see not only how many outcomes there are favorable to rolling a 10. Okay, so the outcomes are I can roll a 4 and a 6, a 5 and a 5, or a 6 and a 4. So there are three favorable outcomes. So probability of rolling a 10 is going to be 3 out of 36. Okay, so pretty easy to compute. Let's get the percentage just for fun. Looks like approximately 8%. And a good follow-up question to this is, what is the most likely roll of the dice? Well, the most likely roll is going to be 7, right? Because it has the most favorable outcomes. It has 1, 2, 3, 4, 5, 6 favorable outcomes. So the probability of rolling a 7 is 6 out of 36, which is about 16%. So actually about twice as likely as rolling a 3. And now if you've ever played the game Settlers of Catan, then this has something to do with those dots that are actually on the tiles that you have to roll. And if you don't know what I'm talking about, that's okay. But the point being that the most likely roll when I roll 2 dice is 7. Okay, so you can just think about what that means in the context of that game. But yeah, so that's a pretty cool experiment, rolling 2 dice, and we can look at a lot of different outcomes, a lot of different events, and compute their probabilities. Okay, so let's switch back to flipping a coin. So let's say I flip a coin 5 times, and I have my coin here. So let me flip it 5 times, and I'll tell you the results. Okay, tails, and then tails, and then heads, and heads, and then tails. Okay, so tails, tails, heads, heads, tails. And I want to know, what is the probability of flipping exactly 2 heads? Okay, well, look, I just did it. So this is a favorable outcome. So my outcomes are going to be just a list of 5 letters, so either T or H. And then if I look at that list, recording all of the outcomes of the individual coin flips, I'm just looking for outcomes that have exactly 2 H's. So in this case, this was a favorable outcome to the event of flipping exactly 2 heads. So let me do it again. So I have tails, 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 heads, and tails. So this particular sequence of flips is not favorable because, well, there weren't exactly 2 heads. Okay. So again, the question is the same. What's the probability of this event? What's the probability of flipping exactly 2 heads? Well, we're going to have to look at the sample space. And again, maybe the easiest way to create the sample space is just to write down every possible outcome. And there's not too many here. Now we will get into later actually counting the number of outcomes. Like I said, we'll get a little bit better at that. We don't just want to have to write down every single outcome every single time for these experiments because they can get very large. But here we actually can. So let's pull up the sample space. Okay, so here's the sample space. Hopefully it's not too small. Hopefully you can see it. But what we want to do, okay, so first notice that this should have every single one of the possible outcomes. So how many are there? Well, again, we're going to talk more about counting later, but for each coin flip, there are 2 options, heads or tails. And we're making that choice 5 times. So we have 2 choices, then 2 choices, then 2 choices, then 2 choices, then 2 choices. So those are going to multiply because these are independent events. We'll get to that later. So it's 2 times 2 times 2 times 2 times 2. So there are a total of 32. So that's 2 to the 5th. Okay, so 2 to the 5th is 2 times 2 times 2 times 2 times 2 times 2. 32 total outcomes in our sample space. And how many are favorable? So we're going to have to look. Here's one. Okay. This is going to be a little trickier than before. So here's another one. Here's another one. Here's another one. And another one. You know what? I am counting 2 tails. No, we want exactly 2 heads. Okay, let's see. There's 2 heads, 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 2 heads. I should be missing one. Here's what. There it is. Okay. Yeah, so I actually know that the answer should be 10. And again, later we'll talk about why we can know the answer is 10. It's related to a certain binomial coefficient. It's actually 5 choose 2. But anyways, ignore that for a second, because you don't need to do that. I mean, that's kind of our heart and soul of our class is we like to be able to see things just by drawing a picture, by writing things out. Well, here's my sample space. You can double check, triple check that I've highlighted all of the possible outcomes in the sample space that are favorable to flipping exactly 2 heads. And how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of flipping exactly 2 heads is, well, 10 over 32. Favorable outcomes divided by the total outcomes, and that is about 31%. So about 31% of the time, if I flip 5 coins, then I'll get exactly 2 heads. Okay, so hopefully that was a good introduction to probability, some different experiments, kind of looking at the procedure of figuring out what the sample space is. That's certainly the challenge. When you're looking at a situation where you want to compute the probability, you want to be able to set up the sample space into kind of equal parts, or in other words, outcomes that are equally likely, and then sort of just count those number of outcomes that are favorable to an event, divide by the total number of outcomes, and that's really the main takeaway with probability. It's once you get the hang of it, it's a very simple procedure, but it's very, very powerful. As we'll see, once we get a little bit better at counting, we can sort of move away from just looking at the sample space and actually just count, okay, what's the total number of outcomes, what's the number of favorable outcomes, and then get probabilities relatively quickly to very complex experiments.